Okay, so our third and final method is our internal rate of return discounted cash flow method. So to get started with this, we need to know, what do we mean by internal rate of return? So here's a definition. You know what to do when you see a definition. You've got to memorize that sucker, right? So the internal rate of return is defined to be the discount rate of a project that makes the NPV equal to 0. So you just got to memorize that. Internal rate of return is the discount rate that makes the NPV of the project 0, okay? And another way to think about it is it's the compound growth rate of an investor's money in this project. So you can think about it that way too. This is also very helpful. So I would recommend memorizing this too. So I'll put here that that's also a helpful way to think about it. So now with that definition in mind, we can look at this mathematically and say mathematically the internal rate of return is the discount rate that makes this equation true. And this is another thing you just have to memorize. It makes the NPV equal to 0. When we have the correct IRR in here, okay, we're going to get 0 for our NPV. So let's say memorize this also. This is important because this is always our first step in applying the internal rate of return method. We set the NPV equal to 0, and then we solve for what's the R or the IRR that makes that the truth, the whole truth, and nothing but the truth. So this is going to give us another way to evaluate our potential projects. So step one will be establish, as usual, our opportunity cost of capital and all the project cash flows, and then we'll solve for the IRR using these cash flows. And what's that going to mean? With the IRR method, if the IRR is greater than our cost of capital, the intuitive meaning of this, which is completely correct, is that our cash in this project is growing faster than our cash would grow at our opportunity cost of capital rate. So that's a good thing, right? We want our cash to be growing fast as possible. So that would mean what? We're going to go ahead with this project, right? Because if we go ahead with this project, our cash is going to grow faster than it would in an investment giving us our opportunity cost of capital. On the other hand, okay, if our IRR is less than our opportunity cost of capital, what's that telling us? That's telling us that our cash is growing slower than our cost of capital. So what should we do? We should definitely not go ahead with this project. We should put our money into our opportunity cost investment instead. So this gives us a really, really nice qualitative way to think about projects. That's the good news. The bad news is the IRR method has really big problems associated with it, so we can't always use it. Problem number one is just like BCR method, it doesn't tell us how much wealthier this project is going to make us. Like same problem we had with the BCR method. But the second one, which is more of a problem, is that we always have to solve this NPV equals 0 equation. And mathematically, this means we have to find the roots of a polynomial or a real equation, which we looked at a little bit in the time value chapter. But the problem here is there might not be a real number solution that exists, and there's going to be more than one root. When we find the roots of a polynomial, there's more than one root, and we don't know which real root is correct. So neither NPV nor BCR have this problem, so they're definitely more robust methods than the IRR method. So let me show you an example illustrating the problem with computing the IRR. So let's say we've got this project. So at t equals 0, we'll make a loan of 100. At t equal 1, we'll get an interest payment. And at t equal 2, we'll get another interest payment, and we'll get our principal repaid. Okay, so with our NPV equation, setting it equal to 0 for the IRR, we're going to get something like this. Minus 100 plus 10 over 1 plus IRR raised to the 1 plus 110 divided by 1 plus the IRR raised to the 2. That's fine. Now let's apply the magic of algebra. Let's multiply both sides by 1 plus IRR squared, and that's going to give us that 0 is equal to minus 100 times 1 plus IRR squared plus 10 times 1 plus IRR plus 110. All right, now this should start to look familiar to you from work you did all the way back in high school. Okay, so this guy here, I've got it again on this page. It's exactly the type of thing that we all were tortured with in high school, or maybe for some of you guys even in grammar school. An equation that looks like this. A parabolic equation, a quadratic equation set to 0. 0 equals ax squared plus bx plus c, except x is just equal to 1 plus IRR. Okay, once we make that little substitution, it's exactly in this form. So to solve this, we've got to find the roots of this second order polynomial, right, or parabolic equation. And how do we do that? We use what we were forced to remember in high school or grammar school, the quadratic equation, okay? And that looks like this. We can always do it by hand with this formula, or we could work in Excel, which clearly we can't do on exams. We could use goal-seek in Excel. And either way, we can find x equals 1 plus IRR, and then, of course, IRR is equal to x minus 1. And we find two roots, two possibilities for IRR. IRR equals minus 200%, that's probably not good, or IRR equals 10%. Okay, so this is getting difficult to do. And for longer duration projects, what if we had a cube term here? Or what if we had non-integer terms? What if this was 0.5? We don't have a quadratic equation for general things like that. So it's hard to find the answers, and we're going to find more than one IRR, and we're not going to know which one is correct. So let me give you one more example illustrating this. So here's a more complicated problem of longer duration. So we have 5 cash flows. We have this -1 at t equals 0, positive, negative, negative, and we want to find the IRR. So we just apply the NPV equals 0. So minus 3024 plus 17,172 over 1 plus IRR, et cetera, you get the idea. Minus 12,000 over 1 plus IRR to the fourth. So now what do we have to find here? We have to find 4 roots of a fourth order polynomial. Okay, we could do this with goal-seek or a graphing calculator, and we could find 4 legitimate IRRs for this. Yikes. Okay, so 4. And you can plug these into your calculator and you will find they all make this equation true. They all make the right-hand side equal to 0, matching the left-hand side. So our problem with this is we don't know which one is correct. And also, if we work with goal-seek, if we start near 66.67, goal-seek is going to converge to this one. If we start near 33%, goal-seek is going to converge to this one. So goal-seek is just going to converge to one of these. We won't even know where the other 3 are or how they exist or anything like that. So that's a big problem here. But there's good news. We have math to the rescue, okay? Mathematicians have found in certain circumstances we can use the IRR. If we have projects like this where we have one negative cash flow and all the rest of the cash flows are positive, or if we have all negative cash flows and at the very end we get one positive cash flow, or the 2 other possibilities, which would be, this would be one negative cash flow here, one positive cash flow here, negative cash flow, negative cash flow, negative cash flow. Similarly here, if these 3 were positive and we had one negative, so we have a total of 4 possibilities that look like these. In these cases, mathematicians way smarter than me have found for us that the correct IRR for this project is associated with the smallest real positive root. So that would mean in a case where we have 4 of these, we'd want to choose the 25, something like that. However, important to note, IRR is not guaranteed to work on projects like this, where in general, we have a negative cash flow, negative, positive. If we have positive and negative cash flows out in the future, it's not guaranteed to work. And if we look carefully at this one, we'll see that's exactly the case. Out in the future, positive, negative. It's only guaranteed to work where we have one negative, all the rest positive, or all negative, one positive, that type of thing. Or, of course, again, vice versa, right? Which would be this one, and then this is okay too. We have here one positive and all the rest are negative. That's going to be fine. And I could draw a similar cash flow diagram here where these 3 would be positive and this one would be negative. So there's 4 possibilities where this will work for us. The correct IRR is the smallest real positive root, but it does not work for these general random positive here, negative, who knows types of projects. So how does that help us? This means that the IRR, it's not good for some projects, but it's going to be very good for things like bond projects, right? Where we've seen exactly cash flow diagrams like this or like this if we're the borrower. So let's put in works for these. Okay, so for a bond project, the yield to maturity now is equal to the IRR. So the yield to maturity is the IRR when, I should say here, we use annual time units. So now we have another way to get the yield to maturity for a bond project. We just get the IRR and that's it. Okay, and remember from our chapter 8C, time value of money, YTM is also equal to the equivalent annual interest rate for bond projects. Also, IRR will work for things like loans, mortgage loans, other loans. So IRR is not hopeless. It does work for a very, very big class of problems, right? Bonds, loans, things like that. But we cannot use it for general cases like this. This would be a good real estate development cash flow diagram. You put in some money now, you get some money back when phase 1 is done, you put in more money to develop phase 2, and then you get more money back when phase 2 is done. This type of thing happens in real estate development all the time. All right, so let's get a little recipe for using the IRR method. And the way this is going to work is if we want to evaluate a project with this method, as usual, first of all, we're going to define our mission. So for our short-term low-risk investor, that was we invest in guaranteed return one-year opportunities where guarantees are strong. And once we know our mission, we find our opportunity cost investment and get our opportunity cost of capital from that. For our short-term investor, opportunity cost investment was that diversified portfolio of one-year CDs or simply shares of the Mint ETF. And the opportunity cost of capital would be the average of the interest rates on the CDs or published rate of the weighted average interest rate of the Mint ETF. So then we want to, just like with the NPV method, find potential projects with similar riskiness. IOHO stands for in our humble opinion. Okay, so this is clearly subjective. Other people might disagree. So we find a potential project that we think has similar riskiness, determine its cash flows. Now that we know the cash flows, solve for the R that makes the NPV equal 0. That is the IRR. And now we apply our IRR rule, which is if the IRR we find is greater than the opportunity cost of capital, that means we're earning, our cash is earning at a quicker rate than it would in our opportunity cost investment, so we want to go ahead. If the IRR is less than or equal to our opportunity cost of capital, we don't want to go ahead. Because if it's less, it means it's earning less than we get if we put money into our opportunity cost investment. And if it's exactly the same, the default thing, the easiest thing is to just put more money in the opportunity cost investment. So let's do our distressed seller example with the internal rate of return method and see how it looks. So our mission, again, is going to be invest in these very low risk 1 year opportunities. And you know the story here. We find our opportunity cost investment and get our opportunity cost of capital from that. And then we're looking around and we find this distressed seller deal. Okay, same story. Distressed seller wants $100 for this bond now, and the bond contract says it's going to pay 110 in a year, and there's no intervening cash flows. So what do we do with the IRR method? We always start with just simply setting the NPV equal to 0 and then solve for that IRR. So what do I have? Minus 100 plus, excuse me, 1110, that's our promised cash flow in a year, which is also risk adjusted because it's a treasury bond, right? It was something that was very, very risk free, so we don't have to risk adjust it. And we divide that by 1 plus IRR, and that's raised to the 1 because it's 1 year out. And so that's going to lead us to 0.0 is equal to what here? 110 over 1, let's see. Let me just take another couple steps to do this. Minus 100 times 1 plus IRR plus 1110. We'll just go slow here, one step at a time. And now we're going to have our 1 plus IRR is equal to 1110 over 100, and IRR is equal to 1110 over 100 minus 1, and that's equal to 0.1, and that's equal to 10%. Okay, so that's pretty good here. Let me just back this out, make this all look a little prettier. All right, so we find our IRR is equal to 10%, and that is greater than our opportunity cost of capital. 10% is, in most circles, greater than 5%. So when the IRR is greater than our opportunity cost of capital, it means if we put our money into this deal, we're going to be earning more rapidly than we would be with our cost of capital. So that means that we want to buy this bond. Okay, and again, this is same recommendation as BCR and NPV. Again, the recommendation should always line up. The numbers will always be different, but the recommendations are going to be the same. So that's good. Okay, let's do another IRR example, just because these have all been a little too simple. So let's start out with our investment mission being similar to above, not identical, but close. So we're going to invest now in very low risk 1 or 2 year opportunities. We go out to bankrate.com, look at 1 and 2 year CDs, and the Mint ETF we can still look at. It's got some stuff that matures in later than a year, so we're going to say it's close enough even for 2 year investments. So we still find that our opportunity cost of capital is 5%. So now we want to know, should we buy a US dollar denominated German government bond that costs 100 and the contract says it'll return back 112 in 2 years with nothing in between. So that makes it a 0 coupon bond. All right, so let's see if we should buy this one. So we're going to do the same thing here. We've got the NPV equation, and for the IRR method, we always want to set the NPV to 0. Okay, so that's going to be minus 100 plus 112 over 1 plus IRR. Now raised to the 2. Now we have something a little less trivial here in this case. Okay, and if we do the algebra on that, let's see if we can do the algebra on that. We have 0 is equal to minus 100 times 1 plus IRR raised to the 2 plus 112, okay? And so then we get 1 plus IRR squared is equal to 1112 over 100, and that's looking pretty good. And I think from that we can get directly that the IRR is equal to the square root of 1112 over 100 minus 1. And if you work that out, you should confirm that you get 5.8%. Okay, so let me put it there, confirm this. Okay, so confirm that at home. Okay, so the IRR in this case, 5.8%, and that is greater than our opportunity cost of capital, which is still 5%. So that means our cash would be growing faster in this investment than in shares of the Mint, than in our opportunity cost investment. So we want to go for it. Okay. So I'm going to pause here, and then we're going to pick up in a second with a real world example. And we'll solve this example, this analysis, should we buy the bond example, using IRR, BCR, and NPV. But let's take a little break right here.